Welcome to our fourth lesson on radicals and surds. Again, this is a revision, so I will be working through this very quickly. A radical is any number under a root sign. For example, root 5 is a radical, and so is root 16. However, a radical that is irrational is called a surd. Obviously, root 16 can be written as 4, and this is an integer, so it's a rational number. But root 5 cannot be written as a over b. So root 5 is irrational, and that's why we call it a surd. And therefore, we can generalize and say that the square roots of non-perfect square integers are surds. So root 2, root 3, root 5, root 6, etc. are surds. Now, an interesting story is about the origin of the word surd. In Arabic, a surd is called al-jadhr al-asam. And when Arab mathematics was translated into Latin in the Middle Ages, the word asam means deaf, and it also means a solid body with no entries to it. The translators took asam as deaf. The word for deaf in Latin is surdis, so hence the origin of the word surd. An interesting point about the history of mathematics and how translation changes things. Still, the origin of the notation, which is the root sign, is believed to be an elongated r for radical. So this is an r, the radical of 2, for example. Anyway, let's move on. You need to remember that root 9 is positive 3. The square root sign is reserved for a positive value. However, pay attention that when you're talking about an equation like x squared equals 9, and when you actually take the square root of both sides, you need to remember that there are two answers, the positive and the negative of the root, which is 3. That's why it is absolutely not acceptable to do this. It's confusing, it's not neat. You can do this in your head. Just keep it in your mind that when you take the square root of both sides, remember to write the positive and the negative answers. Now, the square root of a negative, something like the square root of negative 4, is imaginary. There is no real answer. So this does not belong to the set of real numbers, and we shall not be dealing with it in this course. The cube root of a negative, however, is negative. And you can generalize this, that the even roots of negatives are imaginary, and the odd roots of negatives are also negative. You need to learn the following. The powers of 2. You can pause the video and remind yourself of those facts. When you deal with numbers and you see a 128, you need to know that it is 2 to the 7. And we shall see why in a minute. You need to know these as well. The powers of 3, up to 5, that's enough. And those. The powers of 4 can be derived from the powers of 2, the powers of 5 as well, and the squares and the cubes of the 6 and 7 are generally enough. Now let's talk a little bit about the distributive property. Remember that roots are in a way indices. Remember that the power half is the square root. So the rules that hold for indices hold also for roots. And if we have the root of AB, where A and B are multiplied, we can distribute the root. We can also distribute the root over division. And in the case of, let's say, the square root of 25 over 16, we know that this means that this is root 25 divided by root 16, which is 5 over 4. Now, I would really be happy if I don't see this, and you can do this in your heads. Also, the distributive property works in both directions. So if you find root 3 times root 5, you should know that this equals root 15. So it's a two-way relationship, from left to right or from right to left. I hasten to add, just like indices, the root cannot be distributed over addition. So this does not equal A plus B. Never, ever. This is totally wrong. You cannot distribute roots over addition and subtraction. And if you have any doubts, think about this one. Now, adding and subtracting surds is very much like algebra. So 5 root 2 plus 6 root 3 minus 4 root 2 minus 2 root 3 is simply treated like an algebraic expression with the root identifying the like terms, and this will be 5 root 2 minus 4 root 2 is simply like 5x minus 4x, and this gives you simply root 2. 6 root 3 minus 2 root 3 is also plus 4 root 3. So you only add and subtract like surds. Next, the concept of equality of surds. If you have something like 5 root 2 minus 6 root 3 equals A root 2 plus B root 3, then because of this equal sign, you know that A is 5, and you know that B is negative 6. Simplifying radicals or expressing them in the simplest radical form is a skill that will help us deal with numbers in a more effective way. So when we have something like root 80, we ask ourselves, the 80 is a product of two numbers. Hopefully one of them is a perfect square. And if you're good at your numerical skills, then you would know that 80 is 16 times 5. Now this is good because the 16 is a perfect square. And you can use the distributive property to write this as root 16 times root 5, and this equals 4 root 5. Again, I would really hope that you keep this in your head and that I don't see it. Let's say you didn't know that root 80 was 16 times 5, and you could only think of 4 times 20. Then This is written immediately as 2 root 20. But then you think about the 20 itself. It's 4 times 5. So this equals 2 times root 4 times 5. And the 4 goes out from under the root, but it goes out as a 2 to find this 2 waiting for it. So we end up with 2 times 2, which is 4 root 5. And it's the same answer. Simplifying surds allows us to express a radical in the simplest form and allows us to add and subtract what seems to be different surds, but they are actually like surds, as we shall see in the booklet. Now, rationalizing the denominator is an important skill that we need to learn to simplify expressions. Let's begin by a very simple idea. Let's say you have 2 divided by root 3. In the old days, it was impossible to do this division because they had to do this long division in this form. This is the 2 and 1.73, and this is the irrational. How can you do this division? It was almost impossible. So they decided it's much easier to divide by a rational. And it makes sense, so let's divide by the rational by changing the fraction into a denominator that is rational. Hence the word rationalizing the denominator. That means making the denominator rational. And the concept is that when you multiply a fraction by 1, fraction or any other expression by 1, it does not change. Now in this case, if I multiply by 1, but the 1 takes a different form, let's say it is root 3 divided by root 3. Right? Root 3 divided by root 3 is equal to 1. So this multiplication does not change the value of the surd. So when you do the multiplication, you end up with 2 root 3 divided by 3. And now you can compare the quantities. 2 divided by root 3 is numerically equal to 2 root 3 divided by 3. And if you want to do the calculation, you can multiply 2 times 1.73 whatever, and you can divide that by 3. And if you're not working with a calculator, then this form is easier to deal with. If our example is a little bit more complicated, for example, let's talk about 2 divided by 4 minus root 3. We need to multiply this fraction by another fraction that's equal to 1 such that the root 3 disappears from the denominator. And in this case, we multiply by 4 plus root 3 divided by 4 plus root 3. Keep in mind that this new fraction that we multiply by is equal to 1. But 4 plus root 3 is what we call the conjugate of 4 minus root 3. Why do we choose this? What's so special about multiplying conjugates? Well, the secret is in algebra. It's in the difference of two square multiplication. A minus B times A plus B is equal to A squared minus B squared. So when we multiply the numerator, we get 8 plus 2 root 3. And when we multiply the denominator, this is a difference of two square multiplication. So the middle term disappears. 4 times negative root 3 is negative 4 root 3, cancels out with the 4 root 3. So we only write 16, which is the 4 squared, minus 3, which is the square root of 3 multiplied by itself. And this equals 8 plus 2 root 3 divided by 13. And the original fraction, 2 divided by 4 minus root 3, has the same value as this answer, only the fraction here has a rational denominator. And this concludes our lesson. Thank you very much.